Learning Application 5, Whose Fault Is It? By Jacob Spitaleri, Dinsdale and Don Do. In this application, we have to utilise our knowledge of physics to find out who was at fault in a crash on an intersection on Ballarat Road. We also have to find out if anybody was speeding and who ran a red light. We're given a small sketch of the incident, and we're also given a dynamometer test with a 10 kilogram tyre block. We're also given skid marks, how long they are and the degree they're at. We're also given the weight of the vehicles and the direction the vehicles are travelling. The Audi was travelling south and performs a right-hand turn. The Mitsubishi is travelling straight east, as well as a sequence of the intersection traffic lights. The formulas we're going to utilise the normal force, coefficient of friction, net friction force, net velocity, the total energy, the static friction and the kinetic friction. To find the static friction, we look at our dynamometer test and we can see that its peak pulling force in the static section is 82 newtons, which we then divide by the normal force, which gives us 0.837. We use the same formula when analysing the kinetic friction, where we get our peak in the kinetic section of the dynamometer test, 69.5, divided by our normal force again, which gives us 0.709. We can then use our conservation of energy formula and then make the net force of kinetic energy the subject, which then gives us our velocity, which is 6.99 meters a second. Then from here, we use our trigonometric functions to find the cosine sine, which will give us the horizontal and vertical components. To find the horizontal component, we have 6.99 cos 20 degrees, which gives us 6.57 meters a second. And then for our vertical component, we use 6.99 sine 20, which will give us our vertical component. Now I'm going to pass it on to Riley to talk about the individual velocities.
So now that we're aware of the horizontal and vertical components of velocity once the crash occurs, we can now work out the horizontal and vertical velocities of the individual cars just before the crash, the initial velocity before the crash of that car. Knowing that the mass of one object times the velocity of the same object plus the mass of a second object times the velocity of the second object equals the total mass times the velocity on the horizontal or vertical axes, depending. So to work out for the Mitsubishi, who travels horizontally, we know that the Audi travels at a velocity of 0 across the horizontal axis. So therefore we know that the velocity equals the total mass times the total horizontal velocity divided by the mass. This goes the same for the Audi, where the Mitsubishi travels at 0 meters per second along the vertical. And we can both solve for the initial velocities, which equals 12.32 meters per second for the Mitsubishi and 5.12 meters per second for the Audi. Knowing this, for the Mitsubishi, we can actually solve for the initial speed before the Mitsubishi driver actually broke, just before they broke. So we know, using our idea of energy conservation, we know that the total energy initially is the same as the final energy. And the final energy involves the kinetic energy as well as the net static force as well as the net kinetic force. Now when we put this into our sort of formula, you can simplify this formula shown here, but for the purpose of demonstration, we've included all the values put in, but we get an answer of 17.77 meters per second, or 64 kilometers per hour, which therefore the Mitsubishi is speeding on Ballarat Road with a speed limit of 60 kilometers per hour. So from here, we can actually work out the maximum speed was needed to avoid the crash, just to see if it was the Mitsubishi's fault for speeding. So doing this, we treat the final velocity to 0 across the 10 meters of which the displacement is, to see the maximum speed needed to stop to 0 over across that 10 meters. So the initial speed, the initial here is obviously 12.8 meters per second, which is 46 kilometers per hour. So the Mitsubishi had to be traveling at 46 k's an hour in a 60 zone to stop this crash, which is a bit absurd. I'm now going to hand this to Don, who's going to talk about the final judgment and the traffic lights.
This is Don. I'm going to be analysing the claim of the individual drivers and the traffic light rotation. The accident happened at 3:15 p.m. on Ballarat Road, which is quite busy, and the speed limit there is 60 k's an hour. Let's go through all of the Audi's claim. He claimed that he was stationary at the intersection, which is false. He was recorded to be moving at 18.4 kilometers an hour. Claim number 2, the Mitsubishi jumped the green light, which is false. The Mitsubishi was recorded to be traveling at 64 k's an hour before braking at the braking point, which is quite near the traffic light. The whole thing indicates that the Mitsubishi was already traveling at that speed for some time beforehand, which indicates free flowing of traffic. This does not fit with the narrative of jumping the green light. There is also a waiting time of 5 to 6 seconds between traffic light of Hoadley Court and Ballarat Road, which would be plenty of time for the Audi to make a right turn and the Mitsubishi to completely avoid crashing. Point number 3, the Mitsubishi was speeding, which is true. He was recorded to be traveling at 64 km an hour in a 60 km zone. However, this does not matter at all because the Mitsubishi have to travel below 46 km an hour to even avoid the crash altogether, which is not plausible on Ballarat Road. So all of this evidence point out that the Mitsubishi driver was not at fault and all the fault is on the Audi driver. All of this show that physics
Works.